So welcome everybody on today's webinar on the de-identification. It's called state-of-the-art medical data de-identification and obfuscation. On the organization of the webinar, we will tell you a bit on the background of Johnson Labs, then on what is the motivation for the de-identification, why do we need to de-identify, and what we are able to do, where we are in the state of the art, what we are offering. Then we will walk you through the benchmarks, what is achievable and what we can achieve, and how we can achieve it, and then what is the typical way of running the identification project. We are Johnson Labs. We are people behind Spark NLP. Spark NLP is the most widely used library in the industry. We have developed commercial extension, which is healthcare NLP, finance NLP, and legal NLP. We focus on accuracy. We are now holding 20 top positions in benchmark pay-per-use code. We focus on the speed. We partner with Intel, with NVIDIA, that runs fast even on the single processor. It's built on top of Spark platform, so it's scalable. It runs on, it can process big data, runs nicely on the very big clusters. But it's built for enterprise. We have experience from healthcare industry. We know how to work with the healthcare data, with PHI data, how to even get data from the hospital, etc. And we have internal annotation teams, so it's like quite a few colleagues are working on annotating of internal data, so that the models what we have, they are not publicly available, and this is how we can achieve decent accuracy, and we can build models. We are 7 years on the market now. We have quite a few customers. Out of 8 largest pharma, 5 are our customers. I would like to mention here Providence. Providence, it's we have nice case study for the identification of 700 million nodes. And IQVIA, with IQVIA, we have another case study on the identification of doctor notes in German language. And this is both, it's running in production. All right, so why we need to do the identification in the first case, right? First place. One reason, it's increasing concern with privacy regulations. And there was HIPAA, with HIPAA privacy rule introduced in the beginning of 21st century. Then GDPR, it's younger than HIPAA. It has very strict penalties. If in case of non-compliance, it can be 10 million euros or 2% of the global revenues. And for HIPAA, it can be criminal penalty or civil penalty. And there are other regulations in the other regions, like in Canada, Australia, etc. In the same time, amount of data available, it's increasing exponentially. There is estimated 30% of the data globally, it's in healthcare, and it's growing like 36% year by year, which is higher growth than in financial services or in manufacturing. And why to talk about de-identification and automatic de-identification? It's on improving of NLP capabilities. It's the quality of NLP is increasing. Here's example for name entity recognition. And every year, roughly, it's 0.5% increase of the accuracy. Right? It cannot go above 100%, but it's going like this lately. So let's look to the regulations in HIPAA. HIPAA It's the law, which is another regulation. It's HIPAA privacy rule. In HIPAA, it's stated that there will be another regulation of the HIPAA privacy rule. And HIPAA privacy rule, it says that basically it is not allowed to use protected health information or disclose protected health information except special cases. And the special cases, it is basically like for curing people, running medicine business, healthcare business, or billing, and etc. But you cannot use the PHI data which contains PHI for anything else. However, if you de-identify the data, so you remove the PHIs, protected health information, from the data, it's not anymore covered by the regulations, HIPAA regulations. And it also states how to remove such a protected health information. So there are two ways. One, it's called expert determination. Expert determination, it's using generally accepted statistical methods. And also you need to document how you remove the protected health information. So this is one way. And the second way, it's called safe harbor. The safe harbor, it's basically listed 18 identifiers in the data which needs to be removed. And all of both methods require then there is no information to identify individual, and also there is no reasonable basis to believe that it can be the remaining information can be used to identify individual human. In GDPR in Europe, the situation is similar, although there is no safe harbor rule, but it's more fuzzy, it's more generic. So basically, you need to determine if the data which are there, it's enough to identify person, natural person, and either directly or indirectly, you need to take into account also cost and amount of the time requirement required for identification, and also which technology is available. However, the conclusion is similar. It's that if the data is rendered anonymous, such that the subject is not identifiable, then it's not covered by GDPR. Okay, and the third factor that I was talking about a while ago, it was improving of the accuracy of natural language processing. And first of all, you may be surprised of how inaccurate are humans. Normally, you see that you would expect that almost all personal health information will be removed manually. You employ somebody who will remove it. But this is not the case. This is example from the literature. They did a benchmark, and one person has the 81% recall, so was able to find only 81% of protected health information with two reviewers. So one is reviewing, and the second is checking if all the protected health information are removed. The result was 94%. Natural language processing already surpassed this limit, and Basil, my colleague, will be showing later that the benchmark is 98.2%. Sometimes we have questioned why it's not like 99.999, etc. It depends on the way how you measure it, because if you measure on the token level, that you count how many protected health information they were there and how many were successfully removed, you get this 98%, what I was showing, 0.2, what I was showing in the slide. However, for example, if you count how many sentences were correctly de-identified, means like no PHI leakage in the sentence, then you get figure which is much higher, which is 99 and more %. All right. So second, what we can do in Johnston Labs. So in Johnston Labs, for the identification, we have part of the software which is doing the identification as a input format. There's like many different formats. Let's say most popular, it's PDF. It can be both scanned PDF or it can be machine readable PDF, the searchable PDF. We can de-identify unstructured text documents. We can also de-identify DICOM images, both on the pixel level, so where the PHI is shown as on a picture, and also in the embedded data and the metadata. Then we can identify various types of Microsoft Office, CSV, JSON, all various types of images. In terms of languages, we support more and more languages over time. Now, just beginning of 2023, this few handful of European languages and the English. However, if needed and if we see demand, we train more models for more languages. So on the identification for unstructured text, let me tell you what are the different methods. So first of all, it's masking. So it's replacing of the PHI or personal information by removing and replacing by some constant string. For example, it can be like name or date or this kind of things, or it can be also that you replace it with, let's say, stars, and we can replace it with a constant number of stars in the document. Let's say each token will be replaced by 5 stars, or it can preserve the same number of stars as it was the original token. So for example, for John, we would replace this with 3 stars. For obfuscation and faking, it is you replace the names and dates. The names you replace with a random number from the dictionary, and also, let's say, number of places or names of hospitals, etc. So there is a dictionary with many names and many locations, and it automatically replaces a random number from the dictionary. For dates, it can replace with a random date, or it can replace with the constant shift of the date in time. For documents, which are scanned documents or DICOM images or other types of images, it can mask. And here in squares on the right side, it's shown how does it look like. So, for example, you replace in PDF document the text with a black rectangle, and the same you can do on DICOM image. Okay, thank you. And Basil, over you now.
Thank you, Yuri. This is Basil, head of data science, leading the healthcare and LP team. So let me share my screen. And from this point on, I'm going to zoom in. So I'm going to share some benchmarks at first regarding what we have done so far in the identification solutions at Johnston Labs. And then I also do some code walkthrough and some technical details, how we do this end to end. So in this slide, you see the 7 languages that we support right now. So we have various various set of entities, like we call it sub-entity, 13 entity level. We have a course level, like 7 entity level as well. So this is the most granular version of the identification. By the way, the identification is not just a name identity recognition. Like the table that you see on this screen right now shows the accuracy of the NER models. But when we build end-to-end pipeline, which I'm going to explain in a bit, it is more than the NER. It is including regex, contextual parser, etc. But as you see, we have a nice accuracy almost in every European language, including the English. So when we do when we enrich the identification pipeline, because PHI means that, like, protected health information, we need to detect it at first. So the first stage is name identity recognition, right? But when we do this, it is usually sometimes overkill and sometimes hard to catch all the differences in different languages, because when it comes to age, date, ID, and location, we can even use some lookup tables, some regex rules, and contextual parsers. Contextual parsers is the hybrid NER model, we can say. It is not using any trained model, but it is using the regex but augmented regex. So it's like a regex on steroid, we can say, so that you can specify different rules and then the patterns, so that it can detect additional entities that machine learning based models would miss. So in this table, what we did is, we at first, like, these are the 4 entities that we try to augment with regex and contextual parser. And as you see, if we only use NER pipelines on English, it is, for example, 0.9 average accuracy. But when we augment it with regex and contextual parser, we get 5% boost. In German, it is still the same. For each language, we are getting nice accuracy. And when you do, like, regardless of the type of the entities, because sometimes your use case, the identification use case, dictates that it doesn't matter what type the entity is. Like, as long as you can mask it or obfuscate it, it doesn't matter if it is patient name or doctor name. Sometimes, of course, for the integrity purposes, some like to keep the consistency of the document, you need to replace the same entities with the same fake entities. But when it comes to masking, it doesn't matter. Usually it doesn't matter, as long as you don't miss any sensitive information over there. So that's why we have another metric over there. We call it PHI, because all these metrics belong to, like, age 91%. These are all belongs to, like, per entity accuracy. But when it comes to PHI, it is regardless of type of the entity, which means that 95% of the time we are catching that sensitive entity, compared to 90%, right? The most drastic improvements occurred in location and age, which is understandable, actually, because if you are working on, let's say, German languages, you can augment this with all the German cities, and then when it comes to age, you can add different variation by using contextual parser, and you can get nice boosts, sometimes even more than 10% boost. When you consider the PHI versus granular entity level, the boost is around 45%. So that, which means that we are right now, we can say that in average, we are above 98% right now to detect PHI entity, which means that out of 100 entities, 100 sensitive entities, we miss less than 2 entities at most. So we did this with we compared our solution with the state-of-the-art solutions in the academic benchmarks. So as you can see, like the blue bars represent Spark NLP. So almost every entity level, like 13 entity levels, Spark NLP is already doing better than state-of-the-art accuracies over there. This is our augmented version, which means that not training with new model, but augmenting with like contextual parsers, regex parser, etc. So we are 3% better than the latest academic benchmark right now. So when we do the same for the other languages, like compare the accuracy, when I say accuracy, I'm using accuracy and F1 interchangeably sometimes to make it to simplify. Of course, there is differences, but let's just call it accuracy. Across all languages, we have different but more or less same accuracy across each language. For example, for the name entities, we are around 94 in every language, like 94% in every languages. For the date, it is more than 98, and for ID, it's more than 93. So we have less discrepancies across the languages, which we try to have language agnostic, because we can extend this model, this pipeline, to other languages with less effort, without even sometimes, we are publishing a paper about this, by the way, without even sometimes annotating new data by switching from one language to another. So there are some commercial cloud providers out there, like namely AWS, Google Cloud Platform, and Azure. So they also provide some identification solution, but you need to send your own data, and it's a pay-as-you-go solutions. Of course, sometimes there are some on-prem solutions like private cloud versions of this as well, which you can protect your own data even on their own server, but you need to pay as you go. But in Spark NLP, when you license once, you don't need to worry about, you can parse 1 million records, 700 million records, or even one single, or just one single node, clinical node, you can de-identify this. And when you compare with the other big giant commercial providers, so Spark NLP is beating each one of them, almost every major entity, which is great to see, actually. So how does this work? We have a live app, by the way. You can still go ahead and check right now. You can copy paste your own node and then see how it looks. So it is the.johnsnowlabs.com. You can just go ahead and then test right now or after this webinar. So what we do is, on the left hand side, you just paste, like copy paste or type some text. And then you don't even need to select the language, because we have a language detection module as well. Everything that you see here can work on-prem with no internet connection, in air-gap environment, in high compliance environment, which means that you don't need to worry about if you need to pip install any other library, or if you need a live internet connection. We even do the translation offline if needed. But here in this pipeline, we put language detection, which is an open source component of Spark NLP, before the identification pipeline in the same API. So we get the request from, like, when user submit his text. So we send it to this language detection. We detect the language, as you see on the upper right corner. It says detected language English, and then it pulls the corresponding the identification pipeline. If it is Germany, it's going to pull the German version of the identification pipeline, and it's pretty fast, by the way, because we benchmarked this, so we are able to handle this, like, even if this is a Spark, due to the light pipeline concept and then REST IPR architecture that we are using, you can use this solution in real time with no latency, with minimal latency. Of course, we support the structured identification or obfuscation as well. So which means that if you have a table and then you have the columns with the sensitive data, you can just specify the name of the columns. In Spark NLP for healthcare, you can do this. We have a notebook for this, which I'm going to cover in a bit. You can do the like image-based identification as well. Let's say that you want to extract all the text that is burnt on medical images, or just identify the metadata of the DICOM. Or you have some Excel sheet that you wanna, or docx that you wanna identify. You can use all these modules on the left hand side. So anything that you see is powered by Spark NLP. So this is just the UI that we connected through API. So anything that is running on the backend is the Spark NLP code itself. So on this example, that rectangular area, so just one example, this is the raw text, and on the mask version, we replace all the sensitive information with the type of the entities. And in the obfuscated version, we replace them with the fake version. There are some obfuscation consistency as well to keep the integrity, so that the text doesn't look like obfuscated already. So I'm going to cover that as well. So how does this work in technical? How we build such a pipeline? On the left hand side, you see the diagram. On the right hand side, you see the actual code that we write to run this pipeline. Of course, I simplified the code version. I didn't cover all of the components on the left hand side, but let's go over this diagram on the left-hand side. We have a document. Let's say we have one clinical document. We feed it into the Spark NLP pipeline, starting with document assembler. Document assembler is the gateway to the entire Spark NLP pipeline, so that the rest of the annotators, rest of the modules can start using its metadata, so that it can connect everything together, because it's a pipeline concept that each stage is using the input from the previous stage's output. That's why we start with the document assembler. We split the document into sentences, and then split the sentences into tokenizer. So there are different versions of sentence detection and tokenization, which you can customize for your own use case. Let's say that you have some rules for the sentence detection, or you have no idea, you can just use sentence detector out of the box. It works most of the time, because we have a DL version of deep learning based sentence detector as well as pragmatic version, which is rule-based. In the same way, tokenizer, if you have some custom rules, you can just run regex tokenizer or simple tokenizers. It's up to you. So then we take this, we send it to the embedding stage. So we use clinical embeddings here, but you can use other embeddings as well, which we experimented with as well, but it depends on the context that you are feeding. If this is financial document or legal document, you can use other type of embeddings as well, so that the representation of each token would be more meaningful in that context. So why do we need embedding stage? Embeddings is the representation of the word for this NER architecture, because NER, name identity recognition, is basically the token classification algorithm. So to be able to detect the type of the token, like a classification, like label of the word, because we assign label to each word in a document. There are different approaches algorithmically, right? So we are using two approach over that. The first one is by LSTM CNN char architecture. The second one is BERT for token classification. Everyone knows already BERT for token classification, which is transformer-based algorithm, but the faster version, like we are mostly used by LSTM CNN char architecture, which is quite efficient and fast, so that you can merge more than 50 different NER model in the same pipeline if you need it. So what we do is we get the embeddings from the tokens and then send it to the name identity recognition model on the left-hand side. And it's calculating some other features like casing features, chart character features, etc., and then assign labels to each token. Like John is a P patient, week is a I patient, so it's for the beginning of a patient entity, inside of a patient entity, etc. Then we have a contextual parser. As I said before, contextual parser is a regex on steroid. So you can customize, you can write so complex regex patterns by using prefix and suffixes and then length of the scope, etc., so that if you know the type of the document visually, or if you have some domain knowledge, you can reflect your domain knowledge into the model. Because most of the time in deep learning models, you like, if you pick deep learning, most of the time you don't know what's gonna happen under the hood, and then you have less control over the output. So in our pipeline, we merge deep learning model with contextual parser, which is rule-based, regex matches, which is again rule-based, and chunk merger. So chunk merger is basically taking the output from deep learning-based name identity recognition model, contextual parser, and regex matcher, and then merge all of them so that each token get only one label. There are some prioritization rule in the chunk merger, so that we only get what we need at the end. Otherwise, the weak entities might be returned, etc. Because let's say that age and consider age and date entities, right? They are simple. So if NER fails over there, but if contextual parser or regex matcher catch those entities, you don't even need to check NER label, which might miss this entity given the context. That's why chunk merger has different fuzzy matching or some merging strategies that we prioritize according to some error analysis that we do. Then we send everything to the identification annotator. So far, we tried to extract all the PHI entities, sensitive information. Now we get it. The identification does something on top of this, because it's not just the entities, it also has some hard-coded rules as well inside, which is detecting other like ID number, passport number, SSN number, credit card numbers. These are all well-known structured data that you can specify in the identification annotator, or if you don't do anything, you can even, there are some hard-coded rules already over there. It takes the entities, augment it a little bit with its own rule, and then mask it or obfuscate it. So this is how it looks on the right-hand side, basically. We stage by stage, we connect each annotator to each other, and then we at the end of the pipeline, we have one output, which is the de-identified version or obfuscated version. So to keep the consistency of the document, we have a concept called obfuscation consistency. For example, name consistency. If I'm talking about Jane Doe at the beginning of the document, the next reference to that patient, that name should be same, right? I cannot just randomly replace the name, so the names should be consistent. And for the patient wise or like dog wise, let's say that I have 100 patient and 1000 records for each patient. So if I replace Jane with Mary for patient 1, I need to do this for all the clinical notes belonging to the same patient so that I can keep the consistency, because like the attacker can just check all this if they get the like if somehow they breach into your system and then get all the sensitive information, they shouldn't be able to get back, reverse back. By the way, to be able to do this, we also allow the developers to save this mapping somewhere in like with some key so that they can go back to the original version of the same document, which you can hash. So gender consistency is, if it is, for example, Jane is a feminine American name. So if you want to replace this, it should be like similar, right? So you cannot just replace it with Mike, or you cannot just replace it with any other name, which is like German name, Spanish name, right? So gender consistency, make sure that you replace the female name with the female names and the male names with the male names. Age consistency, by the way, on the gender consistency, how we do this, because we have gender classifier as well, which you can integrate into your pipeline. Age consistency, we specified some age groups. There are already some in literature, there is already some age groups for each patient, what's considered adult, childhood, infant, etc. So we replace the ages with another age from the same group. So if it is 80 years old lady, so we cannot just replace it with like 2 years old lady, right? So otherwise it would it wouldn't be consistent when you read the document. So clinical consistency, again, so like a breast cancer or prostate cancer, right? There are some gender specific clinical issues, diseases that would indicate the gender of the patient, and if you replace that name with another name from another gender, it's a problem. Day shift consistency, you can specify range, you can specify patient-wise day shift. You can say that, okay, all the like patient 1, I will apply +3 days, let's say. Patient 5, I will apply -3 days. So you can apply this, or you can randomize all of them. Date format consistency is if it is European format, US format, etc., or if it is March, like this kind of relative date or partial date, it should be the partial as well, so that to be able to apply this day shift, you need to, if you don't have a proper format dates, you need to normalize them as well. That's why we are using date normalizer to normalize the date and then apply the day shift. And then the last one is length consistency. Sometimes people wants to keep the same length after the identification or obfuscation, so that you need to use the same length names, or at the end, the length of the documents shouldn't change. Sometimes their infra dictates this. So we try to do this as well. So let's do a little bit code walkthrough. I'm not going to run the notebook, but I'm just going to show you how you can run the same notebook that I'm showing here right now. So if you go to Spark NLP workshop repo, you will see this notebook, by the way. It is like let's go. So if we just, I'm not sure if you're still able to see my screen, but Please let me know if you see the workshop repo. Anyway, so if I let me just go here and then run this. So if you go to workshop repo, so under John Snow Lab, there is a Spark NLP workshop repo, and then over there we have a healthcare NLP folder. I'm going to use John Snow Labs library for this. It's a library that is covering Spark, like Visual NLP, Spark NLP for healthcare, Spark NLP for finance and legal, etc., so that you don't need to pip install any other library. So if I go to fourth notebook, it's clinical identification. So this is Jupyter Notebook actually, but you can open this in Colab. So it's going to open up in Colab. So I'm just going to hit open in Colab and it's going to open. So if it doesn't open, let's just copy link address and then run it. So this is a Colab notebook, which means that Colab is, as you know, if you have a Google account, you can, this is a free cloud instance, which 2 CPU and 12 gig memory, so that, which is quite sufficient. So everything that you see in this notebook can run as in that machine. So in workshop before, you will see more than 70 different notebooks that you can test with the other modules we have in Spark NLP. So let me zoom in a little bit. So here what we do, we pip install and then we load the key that we get from John Snow Labs. So you can apply for a license and then you can upload this license key here, and then John Snow Labs library will install everything according to what you have in that JSON file. Okay, so in that JSON file, you will have the key and license. So what we do here is that, like, when you run this, like after a few minutes, the notebook will be ready and then your Spark session will be run. So, and then the next stage is, so as I said, we have different name identity recognition model that you can use in the same pipeline. We sometimes use 4 different NER model, 3 different contextual parser, 5 different regex machine in the same pipeline. So this is like a Lego that you can build your own castle by using, like, picking some models from the over-the-shelf models and then build it like add it into your pipeline and then augment your pipeline and then go back and then fix it, etc. So that back and forth, you will be able to find your best pipeline. But we have one-liner, the identification pre-trained pipeline, that you don't even need to build the pipeline from scratch because we already built that pipeline and then you can use it in one-liner. So if I just go there, so it's just one-liner, as I said, pre-trained pipeline and then name of the pipeline and then the language. When you do this, you will be able to get this in a few minutes. Like, it will be downloaded and then from now on you can use it and then end up with this table. So if I go back and then show how it works, like on the slides, I already showed how it works, right? Like how to build the pipeline. This is entity detection pipeline at first. So the idea is to detect the pipeline. Then we will like one text. These are the entities that I get after I run my pipeline. I extracted all the entities right now. I only use one NER model, as you see, this one, the generic one, which is 7 label version. So what I did is, like, these are the sensitive information. At the first sight, it looks good, right? But in your case, it will be you need much better solutions, right? So that's why we add more NER models to the pipeline, and then more rules. So you can control you can exclude or include some of the entities by whitelisting and blacklisting. Maybe you don't want to obfuscate the profession, or you don't want to obfuscate the age. Maybe the rule says that you don't need it. So you can just add or drop that one. And another one is you define if it is obfuscation or the identification, which is masking, with this parameter. So in the identification module stage, we specify I want masking, which means that replace all the entities with the type of the entities as a mask. Or obfuscate, if you write obfuscate here, it's going to be replaced by the fake entities. You can return the mapping so that you can save it somewhere. You can do a bunch of other stuff here, which I'm not going to cover, but you can go ahead and check our documentation and entire notebook, this notebook, after the webinar. Then you would customize this further by writing some regex rules, like specifying the day shift everything that I explained in the consistency slide is happening with this with the parameter that you are not seeing here right now. So then, for example, re-identification, you can you can go back and then re-identify by using the mapping that I just mentioned. So when you have it, like when you run this, we suggest people to save that auxiliary column so that they can use the same auxiliary column for re-identification so that no one sees that. You can use multiple NER in the same pipeline. Here, like I have one NER, the second NER, right? So then I merge it and then use it. Then I enrich this with the regex rules. So I can just specify some regex rules and then fit it over. Like I can just specify this kind of regex rules and then use it here, set regex pattern dictionary in the identification module. Then it's going to detect those entities that you specified, you control, right? So, so you can run everything in the light pipeline, which is removing the overhead of Spark itself. You can H group, this is how the H group is working. So set H ranges so that I know that if it is H8, it's going to be replaced by something within this within this range. So it will be 5 or 11, etc. So shifting days, as I explained before, that is you can normalize at first. There is a date normalizer in Spark NLP, and then apply shift according to the patient ID. And we have a structured identification as well, which means that maybe you don't have text, but you only have the you only have the table or CSV file that you know which fields correspond to which entity. You can just use this mapping over there, and then from then, so like you can specify which column represents which sensitive information, and then from now on it will be a completely new CSV file with the fake entities. So this is more or less like this. So if we go to the.johnsonlabs.com, this is a live app, as I said before. So you can specify the language or you can just let it go, and then you can test. It's a live app that you get the results right away, right? Okay. So you can test it with you can just type whatever you want here, and then on the left-hand side, right, and then on the right-hand side. So you will see the results right away. Okay. Thanks for joining us today. I hope you enjoyed. You can ask questions through other channels like email addresses or through our website, or reach us out to me and Yuri through LinkedIn as well, so that we can help you guys further. Thank you.
Thank you, Faisal. So now let's consider how is it running the identification project with Johnston Labs, or the identification solution with Johnston Labs. So there are several options. Let me start with the most complex end-to-end white glove de-identification service. We take care of everything from legal analysis, risk analysis, until the operation of the solution. So here is kind of diagram how to explain it. In the first step, we do legal requirements analysis, because there could be something more on top of HIPAA, GDPR, or it can be some other regulations which need to take care of. Then you need to do the risk analysis, consider where are the PHIs, what are the documents, can it leak, or who will be working with the documents, etc. If we need to do expert determination, then we do expert determination. If we need to cover GDPR, we need to document it, etc. Also, in this step, we set up quality assurance strategy and processes. So when it will be in operations, how often we will check the quality, how often we will check the results, what we will do with let's say drift, that there is a shift of the distribution of the input data, and now the input data look different, which then can impact the accuracy of the solution. So this everything is done in the first step. In the second step, we program what we agreed on the first step into software, and do all this obfuscation, all faking, and everything what Faisal was talking about. In the third step, take a sample of data, measure the accuracy, and check that it is in line with expected results. What we set the expectation in step number 1. Then step number 4, it's running the identification pipelines. And step number 5, it is operation. So let's say emergency unblinding. So if there is a request that you need to unblind some of the identified records because let's say patient is at risk, or you need to respond on the request for audits, etc. So this is like end-to-end solution. Depends on the agreement with customer. We can do everything, or some of those steps can be covered by customer and we only support. Depends on the nature of the customer and nature of the required relationship. Then the second option is start with proof of concept mainly to show if it is doable, what will be the results, what will be the accuracy, if everything will work, etc. We did it already quite a few times, so it's a pre-prepared product. It's usually around 1 month, a bit over 1 month, and we have pre-prepared price tag for this. We will assign a team of clinical data scientists, clinical annotator, part-time project manager, and we will run the project. And in the end, you will have the report and this proof of concept notebooks prepared. And the final option is self-serving cloud. It is now in the development. It will be a product which is run from AWS Marketplace and very simple to use. However, with not all capabilities and all everything pipelines. Okay, thank you very much for your attention. And now we can go to questions and answers.
Thank you. Our first question here, how long does it take to run a de-identification project?
So let me take this question. So if we start with a simple project, it's usually 1 month or a bit over 1 month. And then if depends on the complexity, if there is something with a lot of data pre-processing or the data are not in well-documented shape, it can take longer. And also very often the identification project is just first step of larger project, which includes information extraction and some further processing, and it can be proof of concept, like something between 2 and 3 months, if this is such a complex project.
Great, thank you. Our next question here, where should the data for de-identification be located?
Let me take this. So as I said before, everything that you see during this webinar and that you will learn later on maybe by checking the notebooks can run on-prem with no internet connection. So which means that this solution can be deployed on-prem so that you don't need to send your data to anywhere. So you can ship this pipeline within your own environment and then connect your own sensitive data sources and then run it so that you don't communicate. Or if there is some cloud sources that you are using in your private cloud, that you still keep the data on your on-prem. So you have the full control. So we don't even see, because you have the library and you lock us out. You have just to have the license to run the library and then the pipeline. We support you that down the road, of course, to accomplish what you need. But eventually, that's everything is done by you. So you have the data.
Great, thank you. Our next question here, why do you prefer clinical embeddings? Did you test other types of embeddings also?
Okay, nice question. So in the presentation, we see clinical embeddings over there because we were focusing on the medical de-identification. One might say that sensitive informations have nothing to do, have little to do with the clinical, right? Because the age, gender, etc. This could happen in many other documents as well. That's true. We tested with some non-clinical embeddings as well. First of all, embeddings is needed for the token representation for the rest of the model, as I explained during the presentation. So if this is a financial document, you can use financial embeddings that is fine-tuned on a financial document. We are using a like TLDR, long story short, we use clinical embeddings here because the context was clinical, the representation needs to be better. The model is as good as the representation power. That's why clinical embeddings is used, but any other embeddings can be used, but the accuracy will differ.
All right, thank you.